Welcome. So in this lesson, we are going to be covering K-means. So this is going to be the first lesson in unsupervised learning. So we're going to be looking at K-means exactly. So like we always do, we are going to understand the idea behind K-means, how it works, and yeah, just we're also going to like write it from scratch. So from our knowledge of unsupervised learning, we uh, um, sorry, when we're introducing unsupervised learning, we learned that unsupervised learning is different from supervised learning in that in case of unsupervised learning, we are not giving the model any y. So there is no y that the model is going to be working with. We are just going to give it all of the x's, and we are going to allow it to actually look for patterns by itself, right? So now let's look at an example of that. An example of such data is where we have, let's see, x1, we have x1, and we have another column x2, and x1 contains, let's say, 1, 2, 4, 5, and 5, and x2 contains something like 1, maybe 1 again, and maybe 3, 4, and 5, I guess. Now, in supervised learning, you are going to be expecting that here we'll have some y here. I want to use x1 and x2 to predict y. But that's not what happens inside unsupervised learning. In supervised, excuse me, you are going to be expecting to use x1 and x2 to predict some values of y, and you would already, have some instances of y corresponding to each of these x that you are going to train the model on. But in the case of unsupervised learning, we just want to give our model all of these x's, tell it, okay, go ahead and figure something out. And one of the algorithms that help us to do that is K-means. And we use K-means for something called clustering. Clustering. So let's say what we want to do here is we want to cluster each of these rows, each one of them, they have some relationship, right? And we want to actually group each rows based on the way they behave. And this thing actually has this particular concept has a lot of application in things like recommendation system, in um, ad targeting, and something like customer segmentation also. So you're looking for laptops online, and you start to see adverts that you know that tallies with what you've been searching, or you're interested in a particular type of music, and then because you like that particular type of music, you start seeing um other type of music that actually like relates with the one that you like. So that is one of the application of clustering, and also customer segmentation. So one of the ways that we do clustering, one of the algorithm is this k-means that I want to use. So I want to learn to do. So how does k-means work? So let's say we want to apply k-means for clustering this particular this data set here. So the first thing that happens is you must choose. So let's come here and have steps, and step one is going to be to choose the number of k. I'm going to choose the number of k, that is number of clusters that you want to have. So that's like the first step, the important step. So you're saying all of these data sets, I want you to cluster it into three categories, so into three groups. And those three groups are going to be data that is rows that exhibits the same characteristics, basically. So After choosing your number of keys, the next thing that happens is that, let's say we choose 2, k equals 2 in our case here. So we choose k equals to, we'll say, we'll come here and say k equals 2. And that's what we choose. That is, we want to group this thing into 2 groups. The next thing that is going to happen under the hood, in the algorithm, sklearn has already helped us to like package everything together, but this particular explanation is just to help you understand what happens under the hood. So after you choose number of k, the next thing is going to be that we are going to randomly the algorithm is going to randomly initialize k number of centroids. So centroids, you can think of centroids as the middle of a particular cluster. So let's actually plot. Let's draw a chart of this thing. So let's say we have something like this and like this also. And now this is going to be our x1 and this is going to be our x2 here. So x1 goes from 1 to 5. So x1 is going to be 1, 2, 3, 4, and 5. And I think x2 also goes from 1 to 5. That's going to be 1, 2, 3, 4, and 5. Like this. So the next thing to do is we check when x1 equals 1. So we have 1, 1 here. So let me switch this to something like black color. Then here we're going to have when x equals to 1, y also equals to 1, which is this position here. When x1 equals to 2, x2 is equals to 1. x1 equals to 2, x2 equals to 1 is going to be at this point here. Next one is x1 equals 4. When x1 equals 4, x2 equals 3. So 4, 3 is around this area. Should be this place. Then x1 equals 5, x2 equals 4, this area. Hold on, x1 equals 5. So 5, 4 should be here. When x1 equals 5, x2 equals 4. Then the last one is x1 equals 5, x2 equals 5. So that is going to be here. I'm guessing this place. Okay, so the next thing for us to now do is, now we say we are now going to randomly initialize k number of centroids. So we are going to pick any position on this particular chart and call it our centroid. So if we say centroid 1, so we can come here. Let's say we want to say centroid 1. Let's call it C1, and we can pick any particular place on this chart. So for ease of computation, let's choose this same 1 comma 1. So I'm going to say C11 is equal to 1 comma 1, and then C2, or you could call it C12, and that's going to be, let's choose maybe this place here. So that's going to be 4 comma 3. So it means we have 2 centroids now, and those 2 centroids are this particular location is a centroid, and this also is a centroid. So don't forget, centroid is supposed to be, the uh, basically like a center of a cluster in a way, right? So what's the next thing to do? The next thing to do after we've randomly initialized our clusters, our centroid. So the next thing to do after that, which is going to be step 3, let's put that here. So step 3 is going to be to assign, we're going to compute the difference between each of the clusters, right? Each cluster, oh, I'm sorry, each data point and centroid. Then after doing that, what we do is we now assign, we say assign the data to centroid with lowest distance. And it's really very easy. So what does that mean? It means that we are going to compute the difference or the distance between each data point. That is, we're going to say this particular centroid, this triangle, how far is it from this point one? This is going to be 0. How far is it from this one? How far is it from this one? From that one. So it could be something like this. You can come here and say, let's call it D1, D1. So to do that, it is going to be, this is C1 is 1 comma minus 1. So this is for x1, this is for x1, this is for x2, right? So we can come here now and say D1, that is 1, which is this one here. So the formula for this D is actually Cx minus x1 all squared plus Cx2 minus x2 all squared, something like that. So it's easy, it's actually very simple. We take this, subtract it from this, plus this, subtract from this. So that's going to be 1 minus 1 squared plus 1 minus 1 squared. So what should that be? Then we can also get D2, which is going to be for cluster 2. And cluster 2 is 4, 3. So that's going to be 4 minus 1 squared plus 3 minus 1 squared. So here, this is going to be 0, 0, 0 plus 0, that is going to be 0. And this is going to be 4 minus 1, 3, 9 plus 4, 9 plus 4, that's 13. So it means the distance between this purple centroid here and this plus sign is 0 because it's literally on that particular position. Then the distance between this plus sign and this purple centroid, this one, is what? 13. So it means this particular data point is farther to this centroid than this centroid. So it means it should be here, right? And that's the same thing that we do. We compute across board for each one of them. This second one is going to be, let's quickly get that, 2 minus 1, just to give you, plus 1 minus 1 squared. So 2 minus 1, this is going to be 1, because this is going to be 0. So this is 1. Then this is going to be 4 minus, what's that? 2 minus, excuse me, 4 minus 2. 4 minus 2 squared, because C2 is 4. This is C2, 4, plus second one is 3, I think. That is minus 1. 3 minus 1. So here 4 minus 2 is 1. Then 3 minus 1 is 2, 4. 1 plus 4, 5. So this is 5. So 1 and 5, it means this is one that we just calculated, is closer to this point, which the distance is 1, but to this point distance is 5, right? So where should it belong to? It should also belong to this place because it's closer here. Then if you calculate for the next one, which is this particular point here, it's going to be 0 here. For this particular guy, it's going to be 0. I don't need to do that because that's going to be, no, that is wrong. It is not going to be 0. It's going to be 0 here on this second one because that's going to be literally 4 minus 4, no, 3 minus 3. That's going to be 0. But on this side of things, it is going to be um 1 minus 4, 1 minus 4, yeah, all squared plus, what is the second one? 3, no, 1 minus 3, yeah, 1 minus 3 all squared. So 1 minus 4 minus 3 squared, 9, 15. So this is going to be 15. No, 13. 9, 2, that's 13. So this is going to be 13. Like this particular third one. So it means this place should not, this particular data point should not belong to this place because it is 13 places away from here, but it is 0 to this place. So basically, that's how we know, okay, where should we put each one. Now, when we now compute everything, like when we are done computing everything, which is, let's say we have, let's call it A, which is going to be our decision, or C. So where should this one belong to? Well, it should belong to cluster 1. Why? Because D1 is the least, is the shortest. This second one should also belong to cluster 1 because it is the shortest there. Where should this one belong to? It should belong to cluster 2 because cluster 2 is the shortest. And if you compute for this one, it is also going to be cluster 2. Then this last one is also going to be cluster 2. So what have we found out? We found out that these first two guys, for now, should belong to the same cluster, and these ones should belong to the same cluster, and that is round one. So what's now the next thing to do? The next thing to do, because we cannot just take that and say, oh, that is the final correct thing. Question 4 is we compute new centroid by averaging the data within that particular centroid, that cluster, sorry, within that particular cluster. So what do we do? To get a new centroid, we just come here and add, well, there are two values here, right? So we are going to see, these are the two values, these ones. So I'm going to say 1 plus 2 and 3. 3 divided by 2, that is 1.5. So we can come and say, let's call it C12. That's going to be 1.5. Then 1 plus 1, 2 divided by 2, 1. So it means our C12, that is the new centroid. You could call this one here C11 so that you understand. We can call this one C11 and C21. Then here, we're going to call it C12 and C22. So 1.5 comma 1, it means that we are going to move this particular centroid, this triangle, a little bit away from here. That is on X1, it is going to move up a little bit and get into this middle here, this particular middle. That's where we are going to have our new centroid now, around this area here, right? Then we do for this guy also. So we compute new centroid for here. So 5 plus 5, that is 10. 10 plus 4, 14. 14 divided by 3, I think that is going to be 4 point something, I guess. 4 point something. We can come here and connect this and check 14 divided by 3. 4.6. So we can come here and say, let's just say 4.7 comma 3 plus 4, that is 7, 7 plus 5, that is 12, 12 divided by 3, that is going to be 4 if I'm correct. Yeah, 12 divided by 3 is 4. So C 22 is going to be 4.7 comma 4. So it means we take this guy here, this guy that was 4 comma 3 before, we move it 4.7 all the way up. That is, it's going to be around this area here, 4.7 comma 4. 4.7 for x1 is around this place. So comma 4 is around this area. So it means we are going to stay around this area. So this is where our new centroid is going to be. So I can actually come here and remove this guy, remove this guy. They are not our centroid anymore. So these are our centroid. We can also remove this guy here, remove this guy here. So what's now the next thing to do? Begin to calculate the distance between this one and this one, this one and this one. Calculate the distance between this one and this one, this one and this one, then this one and this one, on and on till we find the perfect place to put these centroids that minimizes something called inertia. An inertia is basically the distance between the sum of square of distance between um, the centroid and each of the data points. So once we find that particular location that we need to put this thing and it minimizes the difference between each of these guys, we found the best place for our centroid, and we just assign each of the data points to that particular centroid to form to those particular centroid to form our final cluster, and that is how K-means happens under the hood. So let's go and code it. I hope it makes sense, but it's going to make more sense when we write it now. So I'm going to say from sklearn dot datasets, we're going to be using the load iris dataset. Is it from sklearn dot cluster. We're going to import KMeans. KMeans. We'll import pandas as PD, import numpy as np, import cborn as sns, import matplotlib dot pyplot as plt. I think that's everything. Then the next thing that we are going to do is we are going to set up the data set. So I'm going to say data equals load underscore iris, and we can say as frame equals true. Just grabbing data. Then we can do data.head just to see the head of the first 5 rows of the data set. So yeah, this is the first 5 rows of the data set. So we want to cluster all of these different flowers into a given number of groups. Let's say 3 groups. We want to say, okay, take this entire data set. There are information about flowers. I want you to look at the pattern in it and like cluster or group all of those flowers into 3 groups or 4 groups or 5 groups, however. So the next thing for us to do, really normally you'd clean if it is your normal data, but this is a practice data set. The focus is on K-means itself. So what we are going to do is we are going to initialize. So we are going to say, let's just call it model. So we can say model equals K-means, and like I mentioned earlier, first thing is number of clusters, and number of clusters, let's choose 3 for now. Then we are going to choose this n init, and we're going to say it is auto, because in some version of sklearn it is always on 1. So, and that's going to just be throwing 1 in for you over and over. Then random state, that is going to be 23 to control, to be able to get reproducibility so that you can reproduce this and get the same outcome every time. Then after that, the next thing is that is a model dot fit, and we are going to be fitting data, and we can get our prediction and say print equals model dot labels underscore, and we can print out print. So I'm going to see that it has actually fitted this, and it has classified each of these data points into 4 groups. In fact, we can put that back in the main data. So this particular main data, data.add, excuse me, that's double D. That should not be double D. Add. So now let's put that in there. We can use list comprehension. So we are going to say data clusters equals f string, what is it? F string, f cluster of x for x in preds. So if we run that, we have this cluster 1, cluster 2, however many it is. So I think everything here is cluster 1 for now. So you're going to see that the upper part is majorly cluster 1, then we get cluster 2. So we can visualize this particular relationship. Like we can look at, for example, you can have something like let's say data, let's use C1, let's say SNS dot scatter plot x equals something like sepal length cm, and we can plot that against y equals sepal width cm, and we can pass u, or we, I don't know how to pronounce that, equals breadth, or equals clusters actually. So if we run that, we have an error. It says sepal width double D is not correct, should be single D. Yeah, we're going to see how it has, the kind of clustering that is happening here, right? So we see that in here, we have 3 clusters. This blue cluster, which represents cluster 1, then this green one represents cluster 2, and these guys represent cluster 3. So we are seeing relationship. However, this is not the real relationship that exists, right? Because to actually visualize the relationship, we are going to have to plot all of these 4 columns. In fact, we can look at this on a 3-dimensional chart. Dimensional plot. So we can do, I don't think we have plotly, but plotly.express as px. So we're going to say px dot scatter underscore 3d. Then we say data underscore frame equals data. Then I can just copy this line here, all of this, paste it here. However, I need to pass z. I see z equals petal length cm, comma, and plotly does not use u, it uses something called column. So if I run this and see, it might take a while for the first time. If I run that, I'm going to get some form of 3D chart. Let's wait for it to be done. Okay, right. So here, if I roll this now, you see this is a kind of like a cleaner, yeah, look, and this is like a three-dimensional representation. So we see all of the blue guys, which is cluster one, I think. Then all of the green guys, cluster two, and all of these red guys, cluster three. So we see how this thing has partitioned them across each of those clusters. And another thing that we can look at really is we can actually find, we just choose like arbitrarily, we just choose this number of clusters as three. So sometimes you don't know the perfect number of clusters to choose, but it is actually very nice to know a range of clusters. So if you know a range of clusters and you're like, or you want to know the best cluster to choose, in that case, we use something called Ebo curve. So we use Ebo curve to choose our optimal k. So I'm going to come here and say choosing optimal k with elbow curve. Um, Choosing optimal k with elbow curve. So how do we do that? We are going to, so elbow curve is basically a chart that shows it's a line chart of number of clusters versus inertia. So let me show you what I mean. So let's say I have for some range of k, so I can say my clusters, I want to experiment with clusters between um say least range 2 to 12, I guess. Maybe just 2 to 15. Then what I want to now do is for each of these guys, I want to actually train a K-means model. So how can I do that? I'm going to set up an empty, kind of like an empty bucket, right? So I'm going to call it inertia or inertias. I don't know if inertias is correct English. Then I'm going to come here and say for cluster in clusters, I'm going to say model equals K-means. And we're going to say number of clusters is going to be equals to cluster n init equals auto and random state is 23 and say model of fit data. We might not want to do this, and that's because our data currently, so we should drop, before we do this, we should drop, let me show you what I mean. Our data currently has this cluster thing inside it. Still coming up, coming up, coming up, coming up. But yeah, it's here. So it has this cluster thing, so we need to drop it. I'm going to do data.drop columns because I can go clusters like this. Then in place will be equals to true. So yeah, that's cool. So we are good now. We can now fit data, then we can get our pret. No, we can just get model dot inertia. So if you run model dot inertia, it is going to give you the value of inertia. So we can just append that. So we can say inertias dot append. I'm not sure if that model or inertia is going to be float or a numpy array. We can actually check, but let's just float it this and up. So once everything is done, I can come and just plot a line chart. So I can do plt.plot, and that's going to be clusters versus inertias, and we can go something like this to join it together like this, or like this to like join the whole thing together. Then we can add a title and say plt dot title and say elbow curve of k in range 2, 50. So if we run that, yeah, perfect. So this is our elbow curve, and it shows us okay how inertia, inertia is expected to be dropping, right? So how inertia is dropping as we are moving on. But the important thing is this: which position did we have the last significant drop? For example, this is 2. Don't forget we started from 2. Yeah. So between 2 and 3, it is an extremely significant drop compared to the others. Then between 3 and 4, it is still like a significant drop. But then after 4 here, 4 is the last position where we have any significant drop. And everything from there they just look the same in a way. So um it is not worth it for us to keep increasing this, since it looks like the value of inertia is just consistent across board. So we stop it at 4, meaning that our um, ideal K is 4, right? In this case, which is the place where kind of like the point of inflection. So that's how you know what your choice of K should be. SNS does set style dark grid. So yeah, that is that. So that is how you do clustering with k-means, and what is just left is for you to just go back or just take this and slot in k equals to 4, since you found that that is your optimal k. So just probably come to this place. Where are you? This place, instead of having k equals 3, so here you just say k equals 4 and give that another spin. You have these values now. You can go like this now, and maybe run this, and you're going to see cleaner separation, right? So then you can maybe give this one also a spin, and to see what it's going to look like. But basically, that is how we do clustering with k-means, and you see how we're able to like do something very nice. Here we now have 4 clusters based on the value that our elbow curve showed us. So that is clustering with k-means. I'm going to see you in the next one, where we are going to be looking at clustering with something called db scan. Thank you very much. See you in the next one.